Okay. No, it's. I'm going to go out of slideshow again.
Yeah. All right, so good morning. Our first speaker is Karin Rabe from Rutgers. And Karin has spoken here before. I like to point out when people have come to visit us. Yeah. Karin is a theorist who works on DFT and other things. And she's going to talk to us about magnetic groups.
Mm-hmm. So again, thanks. I love this school. The last time I was here, I did all the practical stuff. Great experience for a theorist. I send all my theory students to come and do it too, so they understand what's happening in the lab. So my assignment is to do an introduction to magnetic groups, magnetic point groups, and magnetic space groups, and classification of electronic states. And this is a big ask for 1 hour. So we'll sort of work on this together, and we'll see how far we get. And I want you to ask questions. I know there's some of you know all of this already. Some of you don't know anything. Some are in the middle. So let's see what we can find out. So I did ask yesterday, all of you are familiar with crystallographic databases, ICSD or Pearson. I assume you're familiar with regular space groups, the 230 space groups at some level. I'm going to stress, if you haven't already visited these sites, I'm going to stress the value of the Bilbao crystallographic server and isotropy for getting information about the 230 space groups. Yeah, you could get it from the international tables, but it's so much quicker now to get it online. I'm also going to assume you're somewhat familiar with band structure, like you know what a Brillouin zone is, and what those letters, a little bit about how we map energies as a function of letters, and maybe a little bit about the symmetry classification of electronic states. And again, for experimentalists, probably that would be come in most frequently if you were thinking about some kind of selection rules, like transitions between one state and another state. Those are governed by the symmetry properties of the state. So if you think about selection rules, you've thought about the symmetry classification of electronic states, at least at some level. So are we good to go? So, now let's implement some of that. You see how some of that knowledge would come into use in everyday life. So let's take a non-magnetic compound like barium, zinc 2, phosphorus 2. So I'm interested in this compound, so I go to ICSD and I put in barium, zinc, and phosphorus, and I ask what compounds are there, and this is what, if you haven't used ICSD, this is what you get on a query like that. And I see that we have here some, I'm going to focus on this I4MM phase. And so that's telling me that this particular composition crystallizes in a phase that has this space group I4/MMM. Okay, and that symbol tells us something about the crystal structure. It doesn't tell us everything about the crystal structure. It doesn't tell us exactly where the atoms are. For that, we'd have to go into the entry, look at the occupied Bykov positions. But knowing the space group, I can then, if I go and do a search and say, show me a band structure for this compound, then the band structure makes sense because I4MMM this symbol tells me the lattice is body-centered tetragonal. And so if I look at the body-centered tetragonal Brillouin zone for the case that C over A is greater than 1, then I see that this is the Brillouin zone, these are the Greek letters, these are the high symmetry paths, and so I can match that up with the path that I see here, and I can see that, I can interpret this band structure. I also notice in the band structure that there are certain points where levels are degenerate. So here, for example, at gamma, this point is clearly at least twofold degenerate, because when you go out from gamma along towards the x direction, it splits. And in fact, this degeneracy is preserved all the way from gamma to z. Also, if I look at the p point, I see also that there's some, some degeneracy in the electronic states at the p point. And if you know a little bit about the irreducible representations of space groups and how wave functions transform under space group operations, you know that you can look up the character, how to look up the character tables that correspond to these different k points, and find that in fact, at p and from gamma to z, there are two-dimensional irreducible representations, which would explain these degeneracies. On the other hand, if you go into Bilbao and or do it by hand, it's easy enough in this case, look at the x point, there's no two-dimensional irreducible representation, so everything has to be singly degenerate. Okay, so again, this is without going into too much detail, this is the flavor of how we kind of use space group symmetries to organize a little bit our understanding of the band structure. You can also, of course, the space group tells you the point groups, right? So you just like strip off the I or the F or whatever, and in the regular space groups, it's super easy. So our space group is 4/MMM, and the point group governs the tensor properties. So whatever tensor properties you have, you can find first, second, third rank tensors, which elements are 0, which elements are equal, which elements are minus other elements. All of that is governed by the point group. And in Bilbao, there's a utility where you can, let's see, the utility is called tensor. It's in the category of solid state theory applications. And if you go to tensor, then you can choose different kinds of tensors. I'm just going to choose equilibrium tensors. And it will tell you, first of all, which, when it's grayed out, that means the tensor is identically 0 by symmetry. And if it's not 0, then you can click, if it's not 0, then you can click here, hit submit, and it'll show you the form of the tensor. Okay? I love this, because when I was a student, we did not have this. We had to do it by hand, which is, limits a lot what you're willing to do or play with or explore. But here, we can just take that out. I mean, I just put in that I also had to, to look up, to do a citation search on a paper, I had to use a paper volume where it would you look up the paper and it lists a bunch of numbers, or the paper, then you have to go to another volume and look up the numbers. And then you have to go to the shelves to find the journals, and then you have to Xerox them with an actual physical Xerox machine, so it's amazing we got any physics done at all, But anyway, so this is, one of my points is going to be that this kind of ready access to information is actually changing the way that we do, that we study solid solids. It's not just speeding it up, it's actually kind of making routine things that we probably wouldn't have done before, because they would have taken too long or been too hard or been too likely to be done wrong even if we did do it. And here it's going to be right. So just as an example here, I mean, this is kind of trivial, but you know, I can tell you for 4/MMM, you know, all the vector quantities are 0, right? It's got inversion. So, and I didn't need M tensor to tell me that, but, you know, to tell me the structure of some third rank tensor, that's pretty cool. Okay, so now you're wondering, where are we, you know, where's the magnetic stuff, right? So, the magnetic stuff is like if you wanted to look at barium iron 2 arsenic 2 instead. So now, you know, you can do the same thing. I type it into ICSD, I get a list, and by the way, I don't know if you were paying attention, but here we have 30 entries that are basically all for the same compound. So like Leslie yesterday was telling you that there's a lot of duplicate, you know, if you count the number of entries, that's not really the number of compounds in ICSD. Important compounds have been, there's been many different structure determinations which are recorded as separate entries in ICSD. So again, sorry, I keep pushing the wrong button. What ICSD tells me is that the space group is also I4/MMM. And the space group is where the atoms are, right? So it's telling me the symmetries of the atomic positions. It's not the fact that the system has magnetic ions, I expect magnetic moments on the irons, is not really coming into this right now. But on the other hand, if I want to answer the kinds of questions that we answered before about the band structures and the tensor properties, then the fact that the system is magnetic and the extra symmetries or the symmetries, the change in the symmetries that come from the fact that these irons now have magnetic moments need to be taken into account in answering, you know, these questions about the band structure and the properties. So how do we do that? So that's with the magnetic, so that's where, now we're finally getting to the magnetic groups. JP's looking at his watch, so, you know, but, oh, good, we're good, okay. So, above, I forgot, the temperature's on the next slide, above 140 Kelvin or something, this compound's paramagnetic. So there's no, the average magnetic moments on the irons are 0, and for tensor properties, it's pretty much the same as if it was non-magnetic. You know, you can use the same utility in Bilbao for I4/MMM. I do want to point out, in case you do not know this already, that a paramagnetic state is not the same as a non-magnetic state in first principles calculations. In a non-magnetic state, you're assuming that the ion has like literally no magnetic moment. But paramagnetic state, the magnetic moments are non-zero, but they're disordered. And you heard yesterday that first principles DFT people hate disorder, right? We can't really easily, you know, compute a disordered system. We have to do like, you know, fake, you know, like different kinds of ordering and average over them or something like that. In DMFT, you can, which is an extension of DFT, you actually can compute correctly paramagnetic states. But in regular DFT, you don't. And so if someone's showing you a non-magnetic band structure for barium, iron 2, arsenic 2, just like ignore it. It's really not, you know, it's really not capturing the right physics. Okay, so below, below the, here's a picture, by the way. These are the pnictide superconductors. I have to look around. Actually, the reason we're talking about pnictide superconductors is I walked over from the hotel yesterday morning with a student who said this is what he wants to hear about. That was you, right? Okay. So here's, there's a bunch of them. We're looking right now at this 122 type of structure, and the iron. It's never clear from these pictures, but the iron ions form a square lattice, and the arsenic or selenium ions are located above and below. So there's a magnetic transition at 140 something, which was reported in this paper. I don't know. Is Jeff here this morning, or did he just come for dinner last night?
I don't think he's here.
Sorry?
He's not here.
He's not here. Okay. Well, anyway, if you were here,
we'll tell him that you cited him.
yeah. You do that. Like, don't want to waste it. So they did the neutron diffraction. I know there's a lot of neutron people out here, and there's magnetic ordering at 142 Kelvin, which is actually accompanied by a structural transition to the FMMM space group. And indeed, if I go back into ICSD and I look at the entries, I can see that at low temperatures, it's reported now in the FMMM space group. And this is the picture from their paper of what the magnetic ordering looks like. And honestly, this is like a ton better picture of the crystal structure as well. You can now almost see, like, that the ions are squared, forming a square array and such like. Okay, everybody good so far? Are we happy with this? All right. So so you see this, see the ordering pattern. So now, now that we have, so let's talk about this antiferromagnetic system. What can we say about the tensor properties? We have to use the symmetries of the magnetic system. And what can we say about the band structure? Similarly, we know the Brillouin zone, from the symbol, we know the Brillouin zone will be face-centered orthorhombic, but these additional symmetries that will be coming from the spins will lead to degeneracies that we can't explain just from ordinary space group symmetries. Okay, so coming back to my first slide, I now got to the point here. For magnetically ordered systems, we need magnetic space groups. So I love that James had the learning goals. So like, here are the learning goals. We've done this a little bit. Well, we're going to do more about magnetic space groups. And again, if you learn one thing in this lecture today, it's that you should be using these online tools when you're doing any kind of crystallographic group stuff. I'm going to show you how, talk a little bit about how you go from a particular state of the system with the atoms in a certain place and the spins in a certain place, like that picture we saw for barium, iron 2, arsenic 2, to get the MSG. And we're going to be doing this for real systems which have spin-orbit coupling. So we're treating the magnetic moments as axial vectors that have a defined direction in real space. And this, I'll show you how to use the isotropy function findSim to find the magnetic space group in that case. Also, given the magnetic space group, how do we find the tensor properties using Bilbao? How do we understand what kinds of degeneracies there are in the band structure? Probably I'm going to run out of time for turning off spin orbit and talking about the extra kinds of symmetry considerations that come in that you heard about for alter magnets. I'll talk a little bit about LSDA, but you might have to do this yourself, or invite me back, or ask me to make like a little supplement to the recording. Okay, so crystal structure is specified by the positions of atoms. Magnetic crystal structure is specified by the positions of the atoms. where some or all of the atoms have a magnetic moment. A magnetic moment is an axial vector. It transforms like a vector under rotations, but it's unchanged by inversion. And in this case where we have a magnetic crystal structure, we have an additional symmetry operation where we change the sign of all the magnetic moments at once. And physically, this can be, this would correspond to an operation like time reversal. Okay, so inversion doesn't flip spins, but time reversal does. So if we look at let's look at a simple crystal, one-dimensional crystal, up and down spins, and the only thing I realized that when I was looking at it this morning, I should have put the lattice constant here. So I'm using here the lattice constant is A is the distance between these two up spins. So the distance between each spin is A over 2. And you'll see, that's actually a fundamental issue that we'll come back in a few moments. But if we look at let's put the origin on the up atom and write the symmetry operations. Oh, okay, always going in the wrong direction here. I think it's this pointer. You got to get a new pointer. I'm going to blame it on the pointer. So we have the identity and any translation through A, because that'll take all the up spins to the up spins, the down spins to the down spins. Inversion. Inversion doesn't change the spin. I can do inversion followed by any number of full unit cell translations. Or I can do time reversal. That's the identity with a prime is identity followed by time reversal. So this is time reversal. If I do time reversal, I flip all the spins, but then if I translate half a lattice vector, I get the state back. And similarly with inversion, if I do inversion and I follow it by time reversal and translate by any half integer displacement, I'll get the thing back. So everybody sees those are the symmetries. And I can multiply, I can find the structure of this new group that now includes this reverse anti-symmetry operation. The main point of this slide is that the unprimed operations form a subgroup of the full group. But on the other hand, if I start multiplying primed operations with each other, I'm going to get unprimed operations. So we get point groups in regular group theory. We get point groups by stripping off the translation parts. So here, we also get magnetic point groups the same way. So the magnetic point group here is E, I, E prime, I prime. Okay? Is this too easy? Oh, anyway. So you feel good about yourself. All right, so there's a lot of writing here, but this is from a useful reference, which is available on the archive called, it's a book chapter on magnetic point groups and space groups. And so he has a section here where he discusses magnetic point groups, and in particular, so the magnetic point group is the orthogonal group of, you take the orthogonal group of d-dimensional rotations, which might include improper operations, and add this anti-symmetry or time inversion or time reversal into the mix. And so there you have, when you have those types of operators, you have 3 types of groups. The most trivial group is the one where you just pretend that time reversal never got in there, and it's just the ordinary group. You also have a slightly less trivial group where time reversal is in, and everything combined with time reversal, is in, and that's all rotations appear both with and without time reversal. And then you have the non-trivial groups where exactly half of the rotations are followed by time reversal and half are not. Those are the interesting ones. The only thing I'm going to say here about the trivial groups is that this group, the first group, is the symmetry group of ferromagnets. Because you can't, if you time reverse a ferromagnet, no spatial operation is going to get you back. Wait a second. Wait, hang on. Never. Let's cancel that comment for right now. I think. Where's my fact checker? Someone is going to heckle me on mistakes. All right. Okay. But anyway, so we definitely have these three. We have these three groups. So let's go on. And so I took this table of magnetic point groups from Wikipedia. So here's our magnetic point group and the subgroups of our magnetic point group. And I want to see, can we figure out, from the international notation, where we are with this. So I have here EI, E prime, I prime. Which group is that? And here I have the crystallographic point groups, the gray point groups where I just threw in time inversion, and I have everybody and everybody with time inversion. And then the non-trivial groups are in the following column. So this group is the group 1 bar with time inversion and everybody with and without time inversion. The notation for that is the gray group 1 bar 1 prime. Okay, you with me? This group is 1 bar. This group is, wait, hang on a second. This group is 1 bar prime, because inversion appears only with time reversal, not without. And this group, E in time reversal, is the gray group corresponding to the crystallographic point group 1. I've added time reversal to this group. So everybody, so this is the kind of thing, like, maybe, hopefully you kind of see this notation. Yeah, Joe.
Okay, so if you have the 4 operations in the bracket,
Right.
then the question mark is then 1 bar, 1 prime.
Correct.
That's the key magnetic group.
Right, well, that's the magnetic point group.
Magnetic point.
Yeah, so that's the name of, this is, so we're sort of matching up lists of operations with the names of these point groups as given in Wikipedia.
And this is not the same as the crystallographic space group.
Correct. Point groups and space groups are, as you know, but I know you want to make sure everybody else knows, are not the same, right? So if I have a crystallographic space group, then by stripping off the translations and looking only at the point parts, I get a group which is called the point group. And so in the magnetic case, I have a magnetic point group where I have operations that have primes on them because they might also include time reversal. Yes?
And so the way I understand it is gray groups correspond to the paramagnetic state of any material, is that right?
Right, because time reversal is an element of the gray group. So if I had any kind of ordered spin structure, pure time reversal will. Oh, wait. I'm talking about point groups, and let's talk about space groups instead of point groups, because I started to get myself confused again. But okay, yeah. I want to be clear. I want to be more clear about that. But just talking about point groups, here we're looking at mathematical structures, and when you do this kind of thing, you also are always interested in enumeration. So how many of these groups are there? There are 122. So you go from 32 point. Oh my God, I forgot to put the numbers on for the space groups. Okay, well, anyway, we'll figure it out somehow. So there's 122 magnetic, three-dimensional magnetic point groups, which are generated from the 32 crystallographic point groups. That's the rest of them. Okay, magnetic space groups. So you can classify magnetic space groups in a very similar spirit. You start with a non-magnetic space. Yeah.
You go back one slide, please?
This one?
So here, everything that you have is red, previous slide. Aren't these also piezoelectric or polar space groups?
Right, so the red is, I wrote compatible with ferroelectricity, but I mean polar. Yeah.
But the piezoelectric portion,
The piezoelectric and polar are not the same.
I know.
Yeah, I know. So I don't have a piezoelectric. I don't. Yeah, the point group would tell me whether it's piezoelectric or not. I don't have a color for that.
So polar is red.
Polar's red. Polar's red. You know, non-zero magnetization is cyan. Purple is both. Okay, so for magnetic space groups, again we have similar. We start with one of the 230 space groups, and think about the so-called magnetic superfamily, where I'm adding in this reversal. I can similarly have colorless magnetic space groups, which are just the ordinary space groups, 230 of them. I have the gray magnetic space groups, where I have all the operations of the space group and all the operations times time reversal. So there are 230 of those. And then I have additional non-trivial black and white magnetic groups, where half of the operations have a prime and half of them don't. And they are written in this form where this is a little mathematical, so I'm not going to try to prove anything here. But the structure of the magnetic group is I take a subgroup of index 2 in the original space group. That's H, so it's like half of the operations that form a subgroup by themselves. And then I have a coset representative, G prime. I multiply, which is not in H. But when I multiply it by H, I fill out the rest of the group. So that's a little abstract. Let's look at it for this, our simple example. So here's our space group. Is this space group colorless? Is the space group colorless? No, right, yeah, because it's got operations with primes on them. It's not just the ordinary space group. Is the space group gray? I'm going to point at you. Is the space group gray? Yeah.
Yes.
Yeah, is the space group gray? So remember, look at for here I'm putting every operation is applied with and without time of inversion.
Yeah, the two on the bottom. I guess I'm gonna.
Well, yeah. So there's two on the bottom with time inversion, but for this to be gray, I'd have to have E NA and E prime NA. Every operation would have to have a non-time inversion and a time inversion counterpart. So here, I would need to have E prime NA, and I don't.
It's not.
Right, I'd need to have E n plus a half, and I don't. That would be a gray group. So this is not a gray group. It's a non-trivial. It's one of the non-trivial magnetic groups. So let's write it in terms of. Let's see if we can write it in the structure. So the space group the relevant space group here is the normal space group where I have atoms on each. Basically, it's the space group where if I had an atom without a spin on each atomic site. So I would have a Rabe lattice of lattice constant A over 2 and no spins. And so I'd have inversion and E and inversion and all these translations. So that's kind of a regular space group. This space group where I've doubled the unit cell is a subgroup of index 2, right? Because half the operations are gone, the half-integer ones with half-integer translations. So H is an subgroup of index 2, and every operation that I've got here is one of these guys or one of these guys times E prime A over 2. That puts a prime on and makes the translation a half-integer translation. So that's the structure of this group. And so I've written it in my non-trivial way. And it turns, and in mathematics, I go back to the article or the mathematics, there are two categories of non-trivial magnetic groups. They're called lattice equivalent and class equivalent. And for our purposes here, there's a little more information than you really need. The main point is the Rabe lattice of G and H the same? Or is the Rabe lattice of H a sublattice of index 2 of the Rabe lattice of G? So in this case, the Rabe lattice of H is a sublattice of index 2 of the Rabe lattice of G. That you can see, right? And so it's a class, it's called a class, this is one of the class equivalent magnetic space groups.
So if this was a ferromagnetic, just all spin up, then it would be the first one, right? Sorry.
I think that's right, yeah. But no, actually, if it was if it was all spin up, depending on what kind of what we mean by inversion, but if we just mean, if inversion doesn't change, let's say inversion doesn't change spins. If it's all spin up, then it's going to be a colorless group, right? Because time inversion kills you. There's no way to get home if you've done time inversion. Yeah, I mean, if you want, for the class 3 groups, it's better to go to higher dimensions. It's hard. I think it's. I didn't try to cook up a one-dimensional example. I could probably do it with like more than one kind of atom or something. But all right. So enumeration. I have to watch the time here because I just love talking about this. I could, could go on forever.
2 minutes or so.
Okay. We started a little bit late, so I'm going to do it because we want time for questions too. I'll pick up the pace here. So enumeration of the magnetic space groups, it proceeds pretty similarly to what we had before. You start with the non-magnetic groups, and you have 230 of those. You have 230 gray groups, and then you have a certain number, which I forgot to write down how many there are in each class, which gives you a total of 1,651 magnetic space groups. This is a very scary number, right? Like, I never wanted to deal with 1,651 space groups when I was dealing with things on paper. Like, what kind of book, am I going to look at? 230 was bad enough, right? But there you could sort of manage with the international table. But now we have Bilbao, so everything you need to know can be easily accessed in the Bilbao crystallographic server. And there's a list, if you go to the website, there's a list on the side where you have quick access to some tables. So if we go to the magnetic space groups, this is the list of magnetic space groups. And the way it's organized is by, you first click on one of the 230 regular groups because I told you the enumeration was based on the regular groups. And then you'll see the magnetic groups that are generated from that particular space group. So we see this table, this is the 230. We go to MMM, which is 69, and click on that. I would love to do this in real time, but I'm chicken, so I did it here. And this is the list that you get. So you're like, huh? First of all, there's a lot of magnetic groups, but that's not surprising because we have to get from 230 to 1651. So, each space group is better have a bunch. But it's a little bit mysterious here because we have this two lists, one listed with respect to the BNS setting and one listed with respect to the OG setting. And what the heck is that? Like, what's going on there? It's just this guy, like, you know, and which of these, where on the list are we if we just want, you know, barium, iron 2, arsenic 2? So in our journey of exploration here, like, this is where you would get if you follow my instructions. And then it's like, what do I do now, right? So I'll just explain very briefly that what this OG BNS business is. It really has to do, it's a classification based on what you consider the primary lattice to be. So if you think that, so the OG classification very loosely says, I think that the Rabe lattice should be what you get if you erase the magnetic moments. In that case, you'd have one atom per cell and a lattice constant of A/2. The BNS system is based on using the Rabe lattice of the magnetic system, the translations of the magnetic system, which in this case is 2 atoms per unit cell. So, and in this description here, there's a little bit of discussion. So in the BNS system, the class equivalent magnetic space group is considered a member of the magnetic superfamily of H. So H just has those translations through A, you know, taking you from upspin to upspin. In BNS, the magnetic translation group is, oh yeah, and in the OG setting, the class equivalent magnetic space group is considered a member of the magnetic supergroup family of the space group G, which is the one that has these Rabe lattice with A/2. Okay? So there's 2 classification systems. I cannot help that. You just have to know Mangan data, which I'll talk about a little bit at the end if I have time, uses BNS. Yeah.
So just to put it in my language, if I have the FMMM space group, and I want to know how can I decorate that with magnetic folder. It's going to be, if you go back to the last slide, it's going to be one of the top or the bottom list, depending on which.
Right. Yeah, well, again, yeah.
Gravity lattice I want to talk about.
Yeah, you have to, right. And again, I'm pretty lazy. I mean, I still, like, I understand this a lot better than I ever did before, but I'm still like tools that will help me, you know, even if I do it myself, I want confirmation from some kind of tool. So I'm going to go to, and help us in getting this sorted out, I'm going to go to Find Sim. And I'm going to say, hey, tell me the magnetic space group. So how many people have used Find Sim? Anybody? Yeah, okay, great. So, so Find Sim's on the isotropy software site, not on Bilbao. You can find it here under space groups and irreducible representations. And what I did, and I literally did it in like 5 minutes, is I just typed in the atomic coordinates of, from that picture. And I say I have 20 atoms in the unit cell, barium, 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 iron, iron. And click to submit data. And when I click, I get I4/MMM. That's the non-magnetic structure. So good, I probably typed the coordinates in right. Half the time I make a mistake and then it comes out like P1 and then I have to go back and figure out where I made the mistake. So now if we now we can include the magnetic moments on iron. Find Sim lets us do that. So you have to put them, I think I took the wrong screenshot. You have to put zeros for everybody. But if you do that and you submit, then you'll get the magnetic space group. This is what you get. Magnetic space group 64.480 CMA.1'_A FMMM. Okay, so how do we interpret that? The list we had before, it claimed that was the list of magnetic space groups. I get a slightly better list if I go into the magnetic symmetry and applications and like say, show me the general positions of the magnetic space groups. And here I just found here's my space group. So this is a unique identifier, this number. This is 480 out of 1651. So this guy is this guy. It's type 4, that makes sense. You know, and this matches up. There's some other kind of notation which matches up with this.
So in the previous slide, you put in the actual order, magnetic order.
I did, yeah. So, and again, I just realized I didn't. For this to work, you have to put in zeros for the non-magnetic atoms. I took the screenshot before I got the. I was too confident. I took the screenshot before I got the thing to work, and then I forgot to fix the screenshot. But you can see I've put in the magnetic moments for the iron atoms, which are these middle guys. Yeah, Joe.
A very practical question. So in the prior image, you have all of the spins either up or down along A.
Right.
Zeros B and C. And is that why you're going to enter it like this and have like 1, 0, 0?
Right. So 1, 0, 0 means along A.
But if you had entered it 0, 1, 0.
That would be along B.
Right. So then instead of the M prime B and prime A, you get different magnetic.
Yeah, it would be a different space group.
Different. Okay.
Yeah.
Because it's orthorhombic, yeah.
Yeah, because you can see here, again, there's, it's probably a little easier to kind of get the idea here. Like here you have F M prime M M, F M prime M prime M. Well, there's a setting, I guess there's a setting issue for orthorhombic also. So maybe, you know, those are not actually different space groups, but now I'm making this up, so you know you'll have to check it. Okay, but let me get to the finish line here, so JP doesn't get too sad. So now once I have the magnetic space group, then I can get the properties using M-tensor. It's really using the magnetic point group, right? So, but I can either find the magnetic point group myself by stripping off the primes, or I can, by stripping off the lattice information, or I can just ask Bilbao to do it for me, and I get, you know, again here, this is the equilibrium tensors for that particular space group. Again, these are the 0 ones. We learned something we learned before that we didn't learn because it wasn't even a property, is magnetization vector is 0. All right, so I told you about the tensor properties in the last minute or so. Let me just give you a flavor of what's going on with the band structure. So electrons in solids, you know, James yesterday emphasized this is all a model. Electrons there's not really single electron. All band structures are completely fictitious, right? Electrons are not independent particles moving in a potential. It's a construct that we use, you know, to help us understand the properties of solids. But in any case, I like this big button too much. Electrons are independent, single particle Hamiltonian with effective potential that approximately incorporates the electron-electron interaction. That's the world we're living in. Electrons are spin-half particles. They should be described by the Dirac equation. But in solids, the relativistic effects are small enough so that you can treat relativistic effects as perturbations through a formal thing called the Foldy-Wolteisen transformation, which gives you an equation that looks like this, where psi is a 2-component spinner, and the Hamiltonian is a 2-by-2 matrix that acts on these spinners. So to understand classify electronic states, you have to understand how electronic states transform under the given symmetries. In normal space group courses, you will learn that how space group operations act on 2-component spinners, and in fact, and in particular, you learn that rotation by 2 pi is not the identity. You have to have, you need to rotate by 4 pi to get the identity when you have this kind of transformation rule. So that's the concept of the double group. And so if I want to describe electron wave functions correctly when I have everything turned on, spin orbit turned on, I gotta use the double group. Double group is scary, but I can now go to Bilbao and look up irreducible representations of the double groups for any space group. So I'm good, like not scary anymore. When I add time reversal, it gets scarier, because time reversal is an anti-unitary operator. And the whole thing with the representations gets complicated. So, and in fact, it gets so complicated that in the past, people never wanted to deal with it. They would just use something called the Herring test to determine when you got additional degeneracies from time reversal. But with Bilbao, we don't have to do that anymore. In fact, in my group theory course, we figured this out, and we're writing a paper about it to spread the word on, this new way of analyzing band structures. So you just go, these things are mathematics, they're not representations, they're called co-representations. So you can look up the irreducible co-representations of the magnetic double group and classify your states that way. Are you excited? Like, this is so cool. Okay, so I'm coming to the end. When SOC is neglected, so now what happens when you turn off SOC? So now again, we're kind of in approximation, we're leaving the realm of physics and just talking about approximate models and their symmetries. You heard from all the ultramagnetism people that when you don't have SOC, then the structure of that 2 by 2 Hamiltonian is such that you can do rotations in real space and spin space independently. And so those are additional operations that are symmetries of the Hamiltonian that are outside the normal magnetic group, and they're incorrectly called spin space groups. Spin groups are something else, but this is now getting into use, and so you can learn, so you can use those additional symmetries to answer questions about the properties in the band structure. I just wanted to say like 2 seconds about LSDA. So does anybody know what LSDA stands for? I didn't write it on the slide. And the theory students should know. I heard there's some theory students here. Theory students, what does LSDA stand for? Okay. Local spin density approximation. So the simplest kind of magnetic, if you're doing a first principles calculation, if you want to include any kind of magnetism, the simplest thing you can do is called a local spin density approximation. The Hamiltonian, basically you have two separate equations. You have two Schrodinger equations, one potential for spin up, the other potential for spin down. It's determined self-consistently through the local spin density functional. And and so all spins are either labeled up or down. And so, magnetic space group, you can think about the magnetic space groups of this Hamiltonian, but like the whole spin nature of the spin is gone. It's like now just a two-valued thing. It could be black and white. And the weird thing is that magnetization is a scalar. Because you only have, it's totally decoupled from real space. So you just have, some abstract, you average up and down and you get whatever you get. So LSDA is a lot weirder than most people realize. There's a lot of extra symmetries that are not that physical that are account for what you're seeing. So just a warning, talk to me about that. So I'm not going to talk about Mangan data, I'm just going to tell you that there is a database where you can look up the magnetic structures where people are collecting reported magnetic structures, and the neutron diffraction people maybe can, say whether there's a better way of doing this or a better database. But if you're looking for magnetic structures and you don't want to go to the original literature, you can try looking in Mangan data. And this entries look like this. Basically, you look it up and it'll tell you, the magnetic space group if it exists and give you a reference. Okay, so that's where we're going to stop. We fulfilled most of the learning goals to some degree, like at least as much as we could in 1 hour without hands-on. What I really should have you do is all get out the computers, and do these searches as we go along. But again, not really enough time for that. But I hope that you now will feel more comfortable giving this a try and seeing that with these tools and a few concepts, so that you understand what you're doing, you will be able to be as comfortable with magnetic space groups as you are with regular space groups. Okay, great. So I guess we have 10 seconds for questions. Or...
All right, thank you. I know we always talk about this, but maybe one year we'll have a theory module.
We could try that, yeah. But yeah, everybody could have done this on, yeah. Right, we could have done this just, with people's laptops, in fact, right?
No.
Should have, again, or we could add a practical.
Yes. Yeah.
Yeah, right, where we all go find the magnetic space groups of our favorite compounds.
Okay, so questions? Yes.
Can you go back to the slide where you had the two different classifications for magnetic space groups?
Yeah, again, I'm going to have to click because I don't want to go through, I don't want to share and unshare and all that stuff.
That's the one.
Which one? This one?
The one ahead of this? Yeah. So, if they both refer to the same physical magnetic space group, why does one classification have more entries than the other? Doesn't that mean that one of them has more information than the other classification?
I think that what you're seeing here is there's actually crossover because I think if you do the counting, what you see here is that the ones that have if you look under the label here, or you look at these labels, this FMM, there's 5 FMMs in each case. In this case here, there's one which is P sub I MMM. So that again, this different kind of consideration of the Rabe lattice actually brings in different numbers of space groups to a given classification here. It'll all add up, like the ones that aren't, because again, here you see that there are things here that are related to CMMM, CMCM that are not here. And again, that's because of the different treatment and the slotting in of the space group. So that's kind of the answer to your question, is that the ones that are missing here in BNS are actually classified with a different space group. So it's not just a nomenclature, it's actually the grouping, the association with normal space groups is different for the two classifications also.
So, just to elaborate on that, if you take the first from each, are these different symmetries? Are these different orders? Or are they the same?
I would actually say that the first 5 are the same.
Same.
Yeah, I mean, in the two
It's just a
classifications.
matter of what periodicity you want to use.
Right, well, yeah, I mean, the thing is that for the first ones, you see that it says translation Gleiche. That means that it means that the magnetic ordering hasn't changed the translation symmetry. So then it doesn't matter, OG or BNS, it's the same lattice. And so it'll be classified with this, it'll sort of be the same classification. It's when the magnetic ordering changes the translational symmetry that the classification changes, because in one case it'll be the symmetry of the translation symmetries of the magnetic state, and in the other case it'll be the translation symmetries of the paramagnetic state where the spins have been erased. In the cases where the magnetic order doesn't break the translation symmetry, it doesn't matter. You get the same answer whether you erase the spins or don't. For kind of obvious when I say it now, but. Yes?
Does this require a commensurate?
I guess that's as far as I got. I mean, I'm not going to say anything about incommensurate magnetic order. Mangan data has incommensurate structures as well, and if you read the article that describes Mangan data, there's a section on incommensurate structures. I have nothing really to say about incommensurate structures right now. Sorry, but yeah. Next, part 2.
In this table, what's the type number? Does it refer to? Type 1.
Oh, so those are the 4 types that we introduced. So type 1 is just a normal, is the ordinary space group. Type 2 is the gray group. And type 3 and 4 are the 2 types of non-trivial groups. In type 3, the magnetic order does not break any translation symmetries. And in type 4, but it breaks rotation symmetries in general. And in type 4, it breaks translation symmetry, but not rotation symmetry. So I guess probably, I think I wrote this down somewhere else. Ultramagnets are like type 3. Right there, because it's the rotation, well, no wait, they're type 4. Okay. Yeah, you have these rotation, you want to have it's about rotation. There's this thing with the rotation symmetries and then the flipping of the spins. Yeah, check with me on that if you need to know. But yeah, that's those types here are those 4 types that we discussed.
More questions?
So for the ultramagnets, do we use any more Hermann-Mogen notation to describe your groups?
Yeah, of course, why not? I mean, the thing is that with the ultramagnets, you have to be careful, right? Because here we're, assuming that we're characterizing the magnetic order, and when you take off spin-orbit coupling, then you don't have any information about the direction. So you can still use magnetic space groups, treating the spin as like an up-down black-white thing. It actually changes the group.
Right.
And so that's more confusing than useful. So when I'm dealing with ultramagnets and symmetry, the only thing you need to know is PT broken? Is spin flip translation broken? I don't actually need any space group symbol stuff. So, sorry?
It's not adding.
Well, it's not adding anything to my understanding of ultramagnetism. And it's confusing because I'm trying to use a magnetic group to sort of, in a kind of, for an honestly slightly unphysical system. Yeah. Oh, okay, last question, or?
Last question. All right. So has anyone gone through and figured out exactly what structure types and magnetic configurations would potentially be ultramagnets?
I think you'll find lists out in the. I mean, you definitely. I mean, it's crazy. Literature is totally crazy, and people like there's new papers every day, and I don't pretend to keep up with that, but I think I've seen these kinds of lists where people try to.
I mean, they should
But again, it's so
just
simple.
be
It's so
some-
simple. You know?
some subset of all these groups, right?
Yeah, yeah, yeah. It's just the ones.
All coded like this is.
You could do that. Yeah, it's just like again, you can take. But you have again, you have to be careful because you're really looking at no spin orbit.
Right.
So again, I prefer when I'm doing my is this potentially an ultramagnet, just to look at the symmetry without spin orbit. You know, look at the symmetry of the system and say, hey, are we? Is this is PT broken? Is ET broken?
Great. Any final question? Student question?
Okay, and thank you, students, for your participation. Really, that was fun. I enjoyed that. More, keep on doing that the rest of the week here.
There will be a test at the break.
Yeah, and if I put you on the spot, I apologize, but you were, you're all, you hopefully you learned something. So,
All right. Thank you, Karin.
This is not my jacket.